What is a rocket but a highly explosive device that's prevented from exploding by slowly releasing its energy? But in the process of releasing this energy in a controlled way, the rocket is capable of controlled flight. This capability, in conjunction with the large amount of energy involved, has allowed us to do some amazing things. From placing communication satellites high above the Earth into space, to delivering bombs to faraway places on Earth. But every once in a while, our amazing rocket malfunctions, and we find ourselves in a position where it could unleash some or all of its energy upon us. Lucky for us, most rockets going into space are required to have what is called a flight termination system. And with a push of a button, all of our rocket issues will go away, including its payload. It takes about 10 minutes for a rocket to get to low Earth orbit. But for the first few minutes after liftoff, the rocket with its massive amount of fuel is a potential bomb to anyone nearby if it doesn't stay on its predetermined course. Launches are carried out in sparsely populated areas for this very reason. However, rockets are very fast and are designed to cover large distances. This sets up a unique situation. That is, no matter where the rocket is launched, there is a chance that it could hit a populated area and unleash major destruction. After all, that's exactly how a ballistic missile is supposed to work. So to prevent a rocket from causing harm if it goes off course before reaching orbit, it must be drained as much as possible of its kinetic and potential energy. And this is the job of the Flight Termination System, or FTS, in conjunction with the Range Safety Officer. This is the person responsible for making a decision to trigger the FTS. Once triggered, the FTS will cause the destruction of the rocket and its payload. Aside from the cost of the rocket, which is fixed for a particular configuration, the rocket itself can be replaced relatively quickly. The same cannot be said about the payload. Payloads range from communication satellites to research and military satellites and spacecraft. This broad range makes the cost of a payload vary a lot, from a few $1,000,000 to more than $10 billion per payload. With that much money at stake, the job of the Range Safety Officer as a trigger person is not to be taken very lightly. So, they have to be sure that there's no way to save the rocket without endangering a nearby population. Once the signal goes out, potentially billions of dollars in years or even decades of development will be lost. As stated earlier, the way to prevent a rocket from causing harm is to drain it of its kinetic and potential energy. The kinetic energy comes from its velocity, and the potential energy mostly comes from its fuel. Terminating the flight of a rocket is not as simple as blowing it up. It's very important that the debris generated by the blast do not travel very far and have very little potential energy when they hit the ground. To drain the kinetic energy from the rocket, two things have to be done. The rocket must stop producing thrust, and it should not be aerodynamically streamlined. To drain the potential energy from the rocket, its fuel and oxidizers must be either dispersed or combusted depending on the type of fuel used. All of these tasks can be accomplished with explosive charges because they are simple, reliable, and have a very high energy to mass ratio. The destruction sequence starts with the Range Safety Officer commanding the ground-based FTS transmitter to send the termination command to the rocket. The FTS transmitter is one of 5 major components of the FTS. The others are FTS receiver, FTS controller, safe and arm device, and the exploding charges. Once the FTS receiver receives a signal from the FTS transmitter, it will forward it to the FTS controller. The FTS controller controls all of the termination explosives on the rocket. The FTS controller also transmits status data to the ground. Explosive charges are placed on key components of the rocket. These locations are heavily dependent on the specific FTS that are used and the type of rocket that is placed on. One such strategic location is the engine. By destroying the engine, we will stop the kinetic energy of the rocket from increasing. Sometimes just the fuel lines to the engines are destroyed. The frame of the rocket is also punctured by explosive charges at various points on the frame. This will cause the frame to suddenly not be aerodynamic anymore and will cause a sudden deceleration, which will put a great deal of stress on the frame of the rocket, causing it to fail and break apart. So destroying the engine and making the rocket frame not aerodynamic, causing it to break apart, will take care of draining the kinetic energy from the rocket. For draining the potential energy from the rocket, explosive charges are placed on the fuel and oxidizer tanks. This will cause the tanks to rupture at specific locations. For fuels that are hypergolic, that is, fuel that ignite on contact with each other, the tanks are ruptured in such a way that both mixtures come into contact with each other immediately. This is done to minimize the amount of non-ignited fuel that reaches the ground because they are very, very toxic. For non-hypergolic fuels and oxidizer, such as liquid hydrogen and oxygen, the tanks are ruptured in such a way to minimize the fluid contacting each other. Since these fluids are non-toxic, will turn into gas and disperse quickly, the main concern is to avoid a large explosion, which would add more energy to the debris, increasing the area in which they will fall. Now, the explosives that are used at various locations on the rocket are not regular explosives that create blasts in every direction. The explosive mostly used is called a linear shape charge. Before we get into why the shape charge is linear, let's first talk about what a shape charge is and how it works. Shape charge, an explosive in which the energy is focused in a particular direction. A shape charge is used when a barrier needs to be breached with a limited amount of explosive. There are many types of shape charges. Here we'll show a common type. First, there is the casing, which will contain the explosive. Next, the housing, which will contain the detonator. Now, the metal liner. The liner material and shape is the most important part of a shape charge. We'll see why shortly. The liner used in this example is made of copper. Next is the main explosive itself, followed by the booster explosive. Finally, the detonator is added. An electrical charge is used to trigger the detonator. The detonator causes the booster to explode with enough force to cause the less sensitive main explosive to explode. As the shock front travels through the main explosive, it squeezes the liner into a thin jet, which is then expelled at very high speed away from the explosive. Without melting, the kinetic energy alone of the liner is now able to cut through a thick barrier at a precise location. Now that we know what a shape charge is, let's look at the linear type. In many cases, a shape charge is made with a cylindrical frame. This configuration will channel the explosive energy into a single point, or more precisely, a small area. Call this one-dimensional exit. A linear shaped charge, on the other hand, is made with a three-dimensional V-shaped frame. A slice of a linear shaped charge looks similar to the cross-section of a normal cylindrical shaped charge. The linear shaped charge works in the same way as a normal one. However, when it's detonated, it will channel its explosive into a line or elongated area instead of a single point. The linear shaped charge used are flexible linear shaped charge. They are usually bent to match the curvature of the tanks that they are attached to. When they're detonated, the destructive force of the explosion will mostly be directed into the tanks. This is important because ideally the breakup of the rocket should be in a controlled manner. So we've covered the function of the FTS transmitter, FTS receiver, FTS controller, and the explosives themselves. The last thing to cover is the safe and arm device. Flying a rocket with an explosive attached to its fuel tanks requires safety on a different level. The first step is to make the main explosive very insensitive. This makes detonation impossible during normal transport, integration, and launch. But with an insensitive explosive, we need a serious shock to detonate it. And that's where the booster explosive comes in. The booster explosive is more sensitive than the main explosive, but it still needs a detonator to trigger it. Finally, the detonator is triggered by an electric current or a laser. The signal to trigger the detonator comes from the FTS controller, and this is the weak point in the explosive train. By design, it's the most sensitive point in the train. A faulty signal from the controller, or even a legitimate one that's sent prematurely while the rocket is on the ground, could be devastating. Having over 700,000 kilograms of fuel explode on the ground because of an accidental triggering is a real risk that's too devastating to ignore. So to prevent the FTS controller from accidentally triggering the explosive, a completely independent device is placed between the detonator and the explosive. This device is called a safe and arm device. Now let's explore exactly how it actually works. Safe and arm devices. A device that protects an explosive from accidentally triggering. Safe and arm devices, or simply SNA, are used to prevent explosive from accidentally exploding. Explosives are very destructive in most situations, so in order to safeguard against accidental detonation, a system must be put into place to prevent this from happening. The system has to be completely isolated and independent from the system that will trigger the explosive. This is where the SNA device comes in. There are many types of SNA designs, so this video would only focus on one generic type. Ideally, the SNA device should be the only device in the triggering chain that's capable of producing enough energy to trigger the booster explosive and consequently the main explosive. The SNA device accepts the trigger signal from the main system and will either generate or allow the high energy required to pass on to the booster explosive only if a set of physical conditions are met. This could be as simple as a mechanical switch or as advanced as velocity, acceleration, air pressure, time, orientation, or other physical parameters. When in the safe mode, the high energy is physically isolated from the booster explosive. This makes it physically impossible for the booster explosive to be triggered accidentally by the main system. The isolation can be a physical barrier blocking the flow of electricity, air pressure, heat, or light from reaching the booster explosive. When the SNA is placed into the armed mode, a physical path is created between the booster explosive and the detonator that will later trigger it. This can be by removing an opaque barrier in case of laser activation, rotating a conductive material into place in case of an electrical activation, or removing a barrier that will prevent heat and high pressure air from reaching the booster explosive. Whichever method is used, when the explosive is triggered by the main system, it will now propagate all the way to the main explosive, causing the explosion to happen. Flight termination system is a part of most space-bound rockets. The amount of energy carried and the fact that there's only a limited amount of control of the rocket necessitates the need to destroy the rocket and its payload if lives or property on the ground are threatened by it. And this is what differentiates a rocket from any other form of human transportation ever devised. Now, I don't know what vehicles we will use to let regular citizens visit other planets on a regular basis, but I'm certain it won't be one that by design requires a flight termination system. I'm Dex DFX for the Celestial Sphere.